Good evening. So I'm going to go ahead and go over some of these problems, or all of these problems in Chapter 8. Some of them are pretty short, simple, but one or two of them is going to take a little bit of time, so we'll look at all of these. So number one is the roller coaster problem. So the idea with the roller coaster problem is you're looking at those differences in height, and let's say you go from this point, here's the roller coaster, you start at this point and you end up at this point. Then you've got a difference in height. Here's a pretty crooked line. Here's H1, here's H2. Okay, so if you look at that difference in height, then that'll tell you the change in the potential energy, because the change in potential energy is mg delta H. That's going to be mg H1 minus H2. Okay. Once you have that, then you do the same thing that we've been doing. The negative of the change in potential energy is equal to, my deltas are not good, is equal to delta Ke. Okay? So you look at the change in potential energy, call the ground 0. You're going from H1 to H2. So U final would equal mgh2. If you go from here, U initial would equal mgh1. And the work done by gravity is the difference, is the negative of the difference in potential energy. So that's equal to negative delta U is equal to mgh1 minus H2. Okay? And from that, you can calculate the change in kinetic energy. I think it's asking you for, determine the velocity at different points along the trip. And this is what you're doing the whole time. You're equating that change in potential energy to the change in kinetic energy. Okay. That one shouldn't give you very much trouble. Let's look at number 2. Number 2 is a pendulum problem. And the idea is, let's say that it's some sort of rigid rod connected to an axis of rotation. Here's some mass m. And you want to give it enough initial velocity or initial speed to where it goes all the way around. I drew it too long, but it goes all the way till it gets up here. Okay? Call this L and call this L. Not to scale. All right. So you look at the difference in height, call this the 0, U equals 0, and then you can calculate what the potential energy is up there. From that, you can calculate the initial velocity you would need to reach this potential energy. Okay, so how much initial kinetic energy do you need to obtain this final potential energy? It's another delta U is equal to delta Ke problem. I don't think you'll have any trouble with that. Number 3. Number 3 is the box sliding along a surface that has some friction. So let's look at the forces acting on the box. There is an applied force. There is a kinetic friction force. It slides through some displacement, call that delta R. And then you have the normal force and mg. Okay? In part A, you're asked, what is the work done by the applied force? Well, it's in the direction of the displacement. That's just Fa delta R, force through a distance. What's the work done by the friction force? It's the negative of that. You have to calculate that force due to kinetic friction. You know how to do that. You calculate that force based on the coefficient of kinetic friction and the normal force, and you look at this force through this same distance. It's going to be the negative of, I don't know if it's moving at a constant velocity. It may not be. So you will have to calculate this force through this displacement. Okay, the force is in this direction, the displacement is in this direction. That is a negative amount of work. That's part B. Part C asks you, how much work is done by the normal force? Well, the normal force is at a right angle to the displacement, 0. How much work is done by the gravitational force? Same thing. The gravitational force is perpendicular to the displacement. No work done by the gravitational force. Okay? The net work done on the object is the work done by the applied force plus the work done by that friction force, and that equals the change in kinetic energy. This is what we keep doing over and over and over again. This is a positive amount of work. This is a negative amount of work. Okay? You can calculate the change in kinetic energy. I don't know if it asks you, let me see, on part, okay, yeah, it just asks you for the change in kinetic energy. That's the work done by the applied force, the work done by the friction force, which is negative. That's going to give you delta Ke. Once you have that, then you can calculate its final velocity because it starts from rest. So the initial kinetic energy was equal to 0. Pretty straightforward problem. Number 4. Number 4 is a little bit difficult, okay? I mean, there's a couple of ways we can do it. I'm going to look at it both ways, and you know, they're equivalent, but they're different ways of thinking about it. Okay, so for number 4, you have an object, and this is like the problem that we were talking about with the pile driver and the I-beam and all that stuff. So here's a spring. The spring's at equilibrium. This mass is hovering above it at, I'm going to call it some distance h. Okay? You drop the mass. The mass falls and it compresses the spring. Okay? So this is a little, you know, this is contrived, obviously, but we're not talking about the collision and all the vibrations and stuff. We're just saying, okay, what happens, let's say the mass falls and it compresses the spring. Okay? I'm going to call that distance that it compresses the spring. So the mass hits the spring and compresses it. Okay? It's now resting on there, and this little bit of distance I'm going to call y. just like I did with the pile driver problem. Okay? So part A says, how far does the object compress the spring? So let's think about the work that is being done on the object. Gravity's doing work, it's speeding it up, and gravity is doing work all the way down through the entire motion. Not only is gravity doing work while it's falling, and then it starts to slow down because the spring is doing a negative amount of work on the mass, and then it finally comes to rest. Okay? So you have the work done by gravity plus the work done by the spring is equal to delta Ke. Okay? So the work done by gravity is equal to mg y. Okay, let me say something about that. That's after contact, okay? That's after, it's just like we did with the pile driver, except this time we have a non-constant force. We have a spring force that goes like the square of its displacement. Okay? So that's the work done by gravity after the collision. The work done by the spring is equal to minus 1/2 Ky squared. Why is that so? The reason you have a negative is because the spring is doing a negative amount of work. I'm just looking at this magnitude of y. Okay, how far it went. That negative is there because I know that spring force is this way. When you do the problem and you draw the diagrams, draw in the forces. I want you to go through this carefully and try to understand what's happening. So, okay. What's the initial kinetic energy? This is right as this mass contacts the spring. That initial kinetic energy is mgh. It's equated, it starts from rest, it's dropped from rest here. I mean, this is a different way of thinking about it, maybe. I'll do it a little bit differently for the next go-round. What's the final kinetic energy? 0. Okay? Ke final is equal to 0. It comes to rest. We're not talking about when it comes to rest and then, it stops and then it goes back up. Okay? We're taking that snapshot right as it comes to rest. All right. So let's set up this equation. I keep losing my eraser. Where'd it go this time? How could the eraser go very fast? Oh. Okay. All right, let me go ahead and erase this. So we have the work done by gravity, mgy, plus the work done by the spring, that's a negative 1/2 Ky squared. Then we have Ke final minus Ke initial, that's delta Ke. So this is equal to negative mgh. Okay? How do we solve an equation like this? This is an equation that's quadratic in y. This is the linear term, this is the quadratic term, this is the constant term. So I'm going to put it in quadratic form, and you get 1/2 Ky squared minus mgy minus mgh is equal to 0. Okay? Okay? Now, another way of thinking about this, and you're going to get the exact same equation is that the change in potential energy, if you look at the system, the change in the potential energy of the spring plus the change in the gravitational potential energy is equal to 0. Okay? Because it started, I'm not going to redraw the figure, but it started from rest and it came to rest. Something brought it to rest. So the change in these two, okay, is going to be equal to 0. What's the change in potential energy? I'm going to leave this up here. What's the change in the potential energy of the spring? 1/2 Ky squared. Okay? It went from no potential energy to a positive potential energy. I'm just making this a number that's positive. This is the distance through which the spring was compressed. What is the change in potential energy for the gravitational potential energy? We actually need the negative of that. So it's minus mg h plus y. And that is all equal to 0 because that's the total distance. It fell from a height h and ended up at some distance y. Okay, so the total distance that the mass moved was h plus y. You get the exact same thing. These two are the same equation. You factor out a negative mg and you get h plus y. Okay? Now, back to this equation. Okay. So here's what we have to solve. This is the quadratic coefficient, this is the linear term coefficient, and this is the constant term. So I'm going to write that out. I'm going to use the quadratic formula. Y is equal to negative b, that's mg, plus or minus, I'll put the square root in a minute, b squared, that's mg squared, minus 4ac. So that becomes a plus. You get a 2 because you're multiplying a half by 4. You get 2k mgh. Okay? And all of that is underneath the radical. Then you have to divide by 2a. So you divide by k. That's how you solve for y. You're going to get a positive value for y. You're going to get a negative value for y. The negative value doesn't make sense for the way we set up the problem. You take the positive value for y, and I'll let you plug your numbers in, but that's how you get it. Okay? All right. Part B. Part B says, well, let's assume that there is some resistive force, like an air drag that's acting on the object as it falls. And it's acting at it's kind of unrealistic, but it's acting constantly throughout that whole motion. So for part B, okay, I'm going to call this WA for air drag, I guess, plus the work done by gravity, plus the work done by the spring is equal to the change in kinetic energy. Well, it goes from 0 kinetic energy to 0 kinetic energy. This is 0. Okay? So we have the work done by the applied force, not the applied force, the work done by the air drag is equal to minus Fa y plus h. Why is that negative? This is a non-conservative force. It's slowing it down the entire way. The displacement is down, that force is up. Okay, so you get a negative here. You get a negative amount of work from this drag force. Okay? We already know the work done by gravity. We already know the work done by the spring force. So you just have an extra term that's this one tacked on to what we had before, and you get a negative Fa y minus FAH plus MGH plus MGY minus 1/2 KY squared equals 0. That's it. Collect terms. And here's what I came up with. 1/2 KY squared plus FA minus MG y plus FA minus MG H equals 0. The coefficient for the squared term remains the same. The coefficient for the linear term becomes that drag force or resistive force, air force, okay, minus mg, and then for the constant term you have Fa minus mg times h. Okay? So you can calculate these coefficients, plug it into the quadratic formula, or plug it into your calculator, however you like to do it, and solve. Part C, well, Part C says repeat Part A except make g, little g, equal to the acceleration due to gravity on the moon. And they mention ignore air resistance, okay? Good. All right. Number 5. So I don't know if you're on the moon, or you in a space station, or are you out on the surface of the moon in your spacesuit and you're doing the problem. I don't know. I guess you're out in your spacesuit. There's no air. Number 5. Number 5 is a skydiver problem. So assume an oval skydiver. Here's the skydiver, and here's the ground, and this distance is h. Okay? So they give you that value. They give you the value for the altitude, and that's when you jump out of the aircraft. Then at some altitude, and I'm going to call it y, you open your chute. So this is where the chute opens. Okay? So the chute opens at this altitude. So we need the final kinetic energy. It's the same thing. It's the work done by gravity plus the work done by that, I'll call it R, that restrictive or resistive force, and that equals KE final, because, I mean, this equals delta KE, but I think we're after KE final, so I'm going to leave it like this, because this, you know, this is KE final minus KE initial, and KE initial is equal to 0. How much work is done by gravity? Well, gravity is acting on it through the entire trip. Gravity does a positive amount of work, right? Okay, it's mgh. That force due to gravity is in this direction, and the displacement is in that direction. What's the work done by this resistive force? Well, there's two parts to that. When you're falling and the chute is not open, you don't have that much force, okay? So during that part of the trip, and this work is negative throughout the entire path, right? Because that resistive force is in this direction, the displacement is this way, so that work is negative. So you get a negative R, I think I called it RC, and that's the resistive force with the chute closed. Let me make that closed. Times H minus Y. That is that distance. That's H minus Y. Okay? Minus R with the chute open times Y, right? Because now the chute opens here, and that resistive force goes up, and it acts through this distance Y. Okay? Once you have that, you know all these variables, solve for the final kinetic energy or the final velocity, whatever they ask you for. In part C, for 5C, solve for Y. You set it up exactly the same, but in part C, you solve for Y given that final velocity. Okay, number 6. I don't think you'll have a bit of trouble with number 6. Seriously. Okay. Number 7. Number 7's the hemispherical bowl. All right. If you can solve for, okay, here's the hemispherical bowl. So an ice cube starts here and it ends up here. All right. You can calculate that initial potential energy. You have some final potential energy. You can calculate the distance through which it traveled. And I think they're asking you for how much work was done by, let me check and see. Okay, yeah, they give you the final speed here. This is work kinetic energy. You have the negative of the change in potential energy is equal to the negative of the change in kinetic energy, but you have an extra term over here. This is the work done by friction. Or let's just call it a non-conservative force. Okay? All right? So you can figure out how much work was done. That work went into the internal energy of the system. Really don't think you'll have any trouble with that. So work on these problems. You know, get them done as soon as you can. If you have questions, email me. I'm around. I'm not leaving the house except every now and then. So to go gather food and fruits and nuts. Okay, see you guys later.